In this video, we're going to apply kinematic expansions to a problem with two rotating frames. So we start with the basic form of the kinematic expansion when we're trying to find the velocity of some point in f. What we're saying is we're finding the time derivative of the position vectors from a point that's fixed in the f frame to the point P. So essentially for the second term, when we say we're finding the velocity of point P in G, what we're really doing is finding the velocity or time derivative of that position vector from G to P. Okay, notice that G would be fixed in the G frame, while P is the point that you're trying to find the velocity for. And similarly, for the third term, the velocity of G in F it's equivalent to say we're finding the velocity of the position vector from a point fixed in F to that G point. Now let's solve a problem when we have two rotating reference frames. So the problem is we have a moving cart that's moving in the horizontal direction, and we have two bars. Bar 1 is fixed on the cart and it's rotating at an angle of theta. And the second bar is attached to the end of the first bar, and it makes an angle of 5 with respect to the position of the first bar. And we have some points at the tip of the second bar. Bar 1 has length k1. Bar 2 has length k2. And we assume theta dot does not equal to 0, theta double dot does not equal to 0, and same goes with phi dot, phi double dot, x dot, and x double dot. And we need to find the angular velocity and angular acceleration of bar 2 relative to f. And we also need to find the velocity and acceleration of point P in f. Notice that we have two rotations in this problem. Bar 1 is rotating and bar 2 is also rotating. So we need to define two new reference frames to define the bars. So 1, let's call that B1, and B2, B3. So B frame is fixed to the pivot and the cart, and let's call that point B. And we have another reference frame that is fixed to the second bar and rotating with the second bar. Let's call that A1, A2, and A3. And we'll define the point, the center of the A reference frame as A. So to find the angular velocity, so for part 1, to find the angular velocity of bar 2 in F frame, we know that the motion of a rigid body, or bar 2, is equivalent to the motion of the reference frame that's fixed to the rigid body. So we can say the angular velocity of bar 2 in the F frame is equal to the angular velocity of A in F. And we can decompose that into two simple rotations. The angular velocity of B in F plus the angular velocity of A in B. So first, the angular velocity of B in F is the rotation of bar 1 relative to the inertial frame. Since bar 1 makes an angle of theta relative to the fixed vertical position, so we have the angular velocity of B in F as theta dot f3. And we also know f3 equal to a3. Similarly, we have the angular velocity of A in B as in, so that's the rotation of bar 2 relative to bar 1. Okay? And bar 2 makes the angle of phi relative to the position of bar 1. So this aligns with bar 1. So we have angular velocity of A in B as phi B3 or phi F3, A3. And this should be B3 instead. So we know the angular velocity of A in F is just the sum of the two simple rotations, which are theta dot F3 plus 5 dot A3. And since we're dealing with the planar motion, planar rotation, so we know A3 equal to B3 and equal to F3. Okay? So we can interchange the vectors F3, A3 with B3. So let's just simplify that. We have theta dot plus phi dot, and it's in the inertial frame. And we also know that we can express in A3 or B3. Now to find the angular acceleration of bar 2 in F, and it's the same as saying finding the angular velocity of A frame in the F frame. And it's equal to the derivative of the angular velocity of A in F in the F frame. So if we were to just replace the expression for angular velocity of A in F, and we'll have angular acceleration of A in F as theta double dot plus phi double dot and F3 direction. Again, you can use A3 or B3 as the vector. Notice we're dealing with simple rotations or planar rotations in this problem, so we don't have to apply BKE to find the angular acceleration. But for more complicated problems in 3D rotations, you'll have to consider and use BKE to find the angular acceleration. Now for the second part, we need to find the velocity of point P in F and the acceleration of point P in F. So let's write down the velocity expansion first. We have velocity of point P in F equal to the velocity of some g in F plus v, velocity of point P in G plus the angular velocity of G in F cross R G P. So for our problem, the G is equivalent to A, which given a small case G is also A. Then we can rewrite the velocity expansion. We have velocity of point P in F is equal to the velocity of A in F plus velocity of P in A plus the angular velocity of A in F cross position vector AP. Then let's work out this term by term. And we'll start with the second term. To find the velocity of A in P, what we're doing is finding the derivative of the position vector from A to P. And we know the position vector from A to P has the expression of K2, A2. And if we were to assume K2 dot equal to 0, we have this term as equal to 0. So what this means is the velocity of point P in A is equal to 0, and P is not really moving in the A-frame. And term 3, we have the angular velocity of A in F cross RAP. And we know the angular velocity of A in F, as we have found earlier, is theta dot plus phi dot in the A3 direction and cross the position vector K2, A2. And we will have an expression for the angular velocity component as in theta dot plus phi dot times K in the A1. Notice A3 cross A2 equal to negative A1. So this is where the negative sign appears. So now for the first term, if we were to find the velocity of point A in F, what do we need? Let's go back to the problem. We know that A is fixed in the B frame. Right, this is a B frame, and A is on top of the bar, so A is really rotating with the bar. So to apply velocity expansion, we'll first write down the velocity expansion in the most generic form. Now this time we have to replace point P with A, and G is the rotating frame, which in this case is really the B. So we have to replace both the capital case G and small case g with B's. So if we were to replace the velocity expansion for point P in F or point A in F, in this case is we have to replace all the letters correspondingly. So we have velocity point A in F is equal to velocity of point B in F plus velocity of point A in B plus the angular velocity of B in F and cross the vector BA. Again, let's work out this term by term. Since we have used number 1, 2, 3, we'll use 4, 5, 6 here. Let's start with term 4. The velocity of point B in F is equal to the derivative of the position vector FB. And let's call F as fixed in the inertial frame. And let's go back to the figure. So B is moving with the cart. And if we were to fix an inertial frame, we can define this point as F, so that we can use just the length x to express the position vectors. So the position vector is x in the F1 direction. And now we know the velocity of point B in F is x dot F1. Okay. Now term 5. The velocity point A in B is equal to the derivative of RBA. Notice that we're starting from a fixed point in the B frame. Then we have K1, B2. And if we were to assume K1 dot equal to 0, we have the velocity of A in B equal to 0. Now term 6, we have the angular velocity of BF cross RBA. And we know the angular velocity of reference frame B in F is simply theta dot B3. And the position vector BA is K1, B2. Then we have this term equal to negative K1 in the B1 direction. Okay, so if we were to add all the terms that we have just worked out, then we will get an expression for the velocity of point P in F through velocity expansion. And you will get the same solutions if you were to apply BK to solve the same problem. And I'll leave the exercise to you. Next, for acceleration expansion. If we were to find the velocity of point P in F, let's rewrite the acceleration expansion first. Again, we can use the same energy that we use for velocity expansion. We are replacing G with A. And the same applies here. The acceleration of point P in F is equal to the acceleration of A in F plus the acceleration of P in A plus angular acceleration of A in F cross R AP. And we have the angular velocity of A in F and the velocity of P in A. Again, you have to replace all the letters. Again, we can work this term by term. We'll reuse number 1, 2, 3 here. We'll start with term 2. And if we're to find the acceleration point P in A, what we're doing is we're finding the derivative of the velocity of P in A. If we were to go back to the first part, when we find the velocity of P in A, we know it's 0. If we make the assumption that K2 dot equal to 0, so the acceleration of point P in A equal to 0. Term 3, the angular acceleration of A in F cross RAP is equal to, we know the angular acceleration of A in F, as we have found earlier, is phi double dot plus theta double dot in the F3 direction. And we know F3 equal to A3 and equal to B3. And we have the position vector from A to P as K2, A2. So to make the cross product easier, we can replace F3 with A3, A3. So we have phi double dot plus phi theta double dot A3 cross K2, A2, and it's equal to the negative theta double dot plus phi double dot K2, A1. Okay, again, the negative sign is the result of the cross product between A3 and A2. Now term 4, 2 times angular velocity of A in F cross the velocity of point P in A. as we found earlier, we know the velocity of point P in A is 0. So we have this term as 0. Now term 5, we know the angular velocity of A in F is theta dot plus phi dot in the F3 direction cross theta dot plus phi dot F3 and cross K2 A1, which is the position vector from A to P. Again, to make the cross product easier, we can replace F3 with A3. And we will get theta dot plus phi dot A3 cross negative theta dot phi dot K2 A1, and then equal to theta dot plus phi dot square K2 A2. So this is term 5. And now we have term 1 left. That's the acceleration of A in F. If you remember, to find the velocity, we applied velocity expansions twice. And for the second time, we have replaced the letters in the generic velocity expansions with this. And to find the acceleration, we will do the same here. Okay, so to find the acceleration of point A in F, let's rewrite the acceleration expansion here. Okay, if we were to replace the letters, and we will get, okay, we're replacing P with A, and we're replacing G with B. Okay, notice that this is a capital case G and this is capital case B. B with P with A, B with F with R, and we're replacing G with B to omega BF B A. Okay, tiny mistake. We're replacing P with A. Omega G F cross omega BF cross omega BF cross R B A. The acceleration of point P in F is the derivative of the velocity of B in F. And from earlier, we know the velocity of B in F is x dot F1. So we have x double dot F1. Now the acceleration of point A in B is velocity of the derivative of velocity point A in B. And as earlier, we found the velocity of point A in B is really 0. So the acceleration is equal to 0 for point A in B. Now next term, we have the angular acceleration of B in F cross position vector BA. And I'll skip the steps here to find the angular acceleration of B in F, and you will find that as theta double dot in the F3 or B3 direction. And since we know the position vector from RBA is K1, B2, so we'll use B3 as the vector for the cross product, and we will get negative theta double dot K1, B1. Now the Coriolis term, 2 times omega BF cross the velocity of A in B. Again, typo. And we know the velocity of point A in B, that's 0. So this term is equal to 0. And last term, the centripetal acceleration, angular velocity of B in F cross angular velocity of B in F, BA. We'll have theta dot B3 cross theta dot B3 cross the position vector from B to A is K1, B2. And we'll get theta dot square K, B2 direction. You know, the acceleration term is really long. But we know the meaning of each term. And we have a lot of zeros. Acceleration point P in F is equal to the sum of all terms.